Thank you very much. Thank you for the very kind introduction. It's a pleasure to be here. So I'm a computer vision person. I'm going to talk about a slightly different side of computer vision from usual, where it's not about visual recognition, it's about trying to do engineering and science. And it's work that we have done with a bunch of colleagues, a bunch of students, Bruno Lecouat, Theo Bodrito, Eboli, Yann Dubois de Mont-Marin, and a bunch of colleagues, Olivier, Flasseur, Julien, Mairal, and Lagrange, and Langlois. And I have many hats, as you kindly said, and I'm going to jump into the thing. I'm going to talk about photography, smartphone photography in particular. So that's the engineering part, and I'm going to talk about astronomy, and that's the science part. Okay, so why would we look at machine learning and physical models of image formation for these problems? So there are a bunch of aspects that are very interesting. We kind of live in the days of... Oh, and please interrupt me if I go too long, because we live in the days more or less of data. You gather huge amounts of data from wherever, and then you go to the deep learning store and you buy the latest box, and then you plug in the data, you press the button, and you hope for the best. In fact, there are many areas where you do have good physical models of what's happening. In particular, we understand image formation. We understand how smartphone cameras take pictures. We understand how telescopes work. We understand all that stuff. So maybe we should use that knowledge. And so we have this reasonable corruption model. So here X is is some kind of latent perfect image. Y is the thing you observe. A is some corruption operator. So for example, this could be a blur, and epsilon is a noise. And so what you want to do is an inverse problem. You are given Y, you want to recover X. Okay? And again, because we have a relatively good physical models of things, you can use prior knowledge, you can use the model. We can also use things that we know about images. So we know that images admit pretty good sparse models from data. We know that in images you have cell similarities and all that. Also, because we have a very thick model, in vision nowadays people do a lot of simulated data for training. But the simulated data for recognition is often not very realistic. You get flying chairs, you get things like that. They don't look like anything you will see in real life. In this setting, because you have a very strong model, it's easy to generate millions of simulated training examples. Also, instead of just having the black box, we can leverage